Lattices in the plane can take various shapes, even after we allow rotations and scaling. How can we smoothly change the shape between them? A first way is to slide the points to the right or left, with the speed depending on the height. The points on the central axis stay in the same place. All other points will disappear off to infinity. Yet as they move, the points on each line reach the next point along, so the lattice comes back to its original shape. So this deformation is periodic on the lattice shape. We can also start from a square fundamental domain. That is a region which can be attached to every lattice point to give a tiling of the whole plane. This domain is deformed to a parallelogram with the same base and same area, but increasingly slanted sides. After some time, we can choose a new square fundamental domain. Here we actually go through 3 periods of the deformation before resetting the domain. Another smooth change is a rotation, like the stars revolving around the pole star. If the points follow circles, the lattice does not change shape. But they can also follow ellipses. In this case, after some time, not just the lattice, but each individual point comes back to its initial position. As a result, a fundamental domain will also return to its initial shape. There is a third, more mysterious way to deform a lattice. Crush it in one direction and let it expand in another. Individual points will first approach the center, coming from the contracting direction, and then flee it, escaping in the expanding direction. They will follow hyperbolas, admitting these directions as asymptotes. If the directions are well chosen, each of these hyperbolas will contain infinitely many points of the lattice. Here again, individual points escape to infinity, yet the initial shape of the lattice is eventually restored. But this is not obvious if we follow the deformation of an initial square. It is soon changed to a very flat parallelogram, crushed in the direction of the expanding line, and we need a very drastic change to recover the initial shape. And now for something completely different. Consider an L shape made of 2 rectangles. We modify this shape a bit like a baker by crushing it in the vertical direction and letting it expand in the horizontal direction, so that the area always remains the same. When the big rectangle becomes too big, we cut a portion on the external side and stack it on the small rectangle. This is exactly what mathematicians call the operation, cutting and stacking. We can then continue as long as the big rectangle does not disappear when we cut. Here, because the dimensions have been cleverly chosen, we soon recover the initial situation so that we can continue indefinitely, always recovering the same figure. If we want to keep a memory of what we have done, we can make a kind of layered pastry or taffy. Keeping the initial colour, we get an interesting sequence of colours, which is the same on both sides, except for the first 2 levels. Mathematicians call this a Stermian sequence. How does this help with the hyperbolic deformation of a lattice? Come back to the previous picture. Points move on hyperbolas, and a most important element of the figure is given by the 2 black asymptote lines. Things become simpler if we change our viewpoint and rotate these asymptotes to take them as axes. The lattice is now crushed vertically and expanded horizontally. We could, as before, take a square fundamental domain and follow it as it is crushed to a very flat parallelogram. Yet, in this picture, it becomes clear that vertical and horizontal lines are preserved, so we can use an L-shaped fundamental domain with those directions. As the lattice is crushed, the domain is compressed in height and expanded in width. With a suitable fade of colour, we can highlight how the lattice returns to itself. So we shall study this fundamental region in more detail, starting by zooming in. Instead of the fading colours, we can focus on a central region, cutting and moving our focus as it gets too wide from the flow. The periodicity becomes clearer if we pause when the lattice returns to the original shape, then cut and stack. We now note that the region that fades out is always the same as the one that fades in, so we can move it instead of fading. With this shifting, we have a unit that returns to itself, rather than needing pieces that flow into place before disappearing off to infinity. This transition from the L shape to itself is the cut and stack operation we showed earlier. Note that we made a very specific choice here, with the starting ratio of the width of the left piece to the right being the golden ratio. Other specific ratios will give different patterns of stacking, and in most cases will never actually return to the original state.